All right, let's do that. Okay. Yeah, so welcome. Again, if you're just jumping on, there is a file on Canvas called Regression Friday. So we're gonna eventually turn to that file. So if you want to pull that down and follow along, you could go grab that. Yeah. So today our goal is to introduce the idea of regression. Take us from correlation into regression, and set us up for interpreting regression and next week. So again, we go through kind of next Wednesday, but over the next number of days and into next week, we'll be able to kind of talk more in depth about some of the important caveats involving regression and then multiple regression. So a little bit from chapter 14 we can touch on next week. But for today, largely what I want to accomplish is have us understand how do we calculate regression, what is kind of the overarching concept, or what are we trying to do in regression, and then that'll set us up for, again, kind of a more flexible discussion next week. Yeah. So before we delve into regression, let's come back up to speed from where we were on either Monday or Wednesday, the earlier lecture this week, and discussing correlation. And as I said during that lecture, that correlation has a couple roles, and one of which is to be the foundation of this powerful tool that we call regression. So but the other one, again, is that we use correlation to just talk about the relationship between two variables. So it's a very good descriptive statistic. It summarizes the relationship between two variables quite quickly and quite effectively. So I should be more specific. It summarizes the linear relationship. Okay, so that's one of those caveats that we'll talk about next week, is that the methods that we're talking about here are all about lines. They're all about linear relationships, and so they don't pick up, other types of relationships. So, but this can be very helpful. So we're going to jump back and talk about the example we worked on with correlation, and that was this kids and milk. So let me pull that back up. Let's see if I have a clean place to start. Well, we can just rehash where we were with this overly gross that. So we'll pick up right where we were with 73 different colors on the screen. But just to ramp us back up to speed, remember we talked about this example where we had data specifically on maybe this will be helpful. We had data on just these 4 households. Okay, so we had 4 households that we knew the number of kids and the number of gallons of milk they drank per week, and we wanted to be able to describe the relationship between these two variables. And just by plotting it, we could see that there's probably a positive relationship, but can we put a numerical value on that? Can we discuss the linear relationship between these two variables more definitively? And so we went through this somewhat tedious example of calculating the deviations from the mean, right? So to rehash, this is all about deviating from the mean, but we're doing it now in 2 directions. Okay, so we're taking into account how do these variables interact, or how do they deviate or move away from the mean of that variable. So we're calculating, okay, this data point is 3 3 units below the mean in the number of kids, and it's also 3 units below the mean in milk. And so we can use that information to weight the different deviations from the mean. Okay, so we went through that whole big process, and we found we were able to eventually calculate that this is a positive correlation, like we expected. It's a positive, and it's also we put a value on it of 0.8366. Okay, so a strong positive relationship between the number of kids and the gallons of milk drank per week. Okay, so what I want to do now is I am going to turn to that Excel file. So again, if you've just jumped on, I've got it posted on Canvas, so you can pull it up if you'd like to follow along. If you don't want to just watch, that's fine, but it'll be there after we're done too. So this will be cleaner than the scribbles that I have up here. So let's turn to that now, or let's turn to it as soon as I can click the right buttons. And let's just do that. Will work. I think that'll work. Well, I'll come back on the screen, at least until the computer yells at me for overloading it. And we'll try to. Yeah. Okay. So I have this this pulled up, and again, so what do we have? We have the same data. Okay, so I'm just recreating much of what we scribbled on the purple board the other day. But we can see a little bit how Excel can do this for us, and probably a cleaner way than my penmanship. Okay, so we have our data, kids in milk. We can take the mean and the standard deviation like we've always done, but we can go ahead and do the same by hand crunching. So I'm just going to quickly do that to show you that that's possible, right? But and to kind of rehash this, right? So X. We're just going to set that as kids minus the mean of kids. Okay, so that's that -3 that we had calculated. If I lock this in, right, using the $sign. I know we haven't been in Excel all that often, but remember that $sign locks it in, and so I can pull down, and I have that deviation from the mean for each observation. Okay, so if we look down at the scatter plot, I've added in this mean point. Okay, so that's not one of our actual data points, but like we talked about the other day, it's often helpful to have that as a reference. And so we can think about this column that I just made, -3, -1, 1, and 3, as the deviation. So this here is -3. It's 3 units below the mean, 1 unit below the mean, 1 unit above the mean, and then 3 units above the mean. Okay, and in our calculation, this is maybe a little different order than we did on the purple board, but we can calculate the standard deviation right along here, right? So the sum, we're going to sum up all of those squared deviations. Okay, so that's the 20, and then we're going to take the square root of those sums of deviations, squared deviations, sorry, and then divide by n-1, which in our case is 3. Okay, and we get the 2.58, just like we did over here. Okay, so that's bringing back up stuff from whenever that was, chapter 3 or chapter 4. Okay, so again, same with the y bar. We can do y minus the mean of y bar. I'm going to lock that in with a $sign, so I can simply pull this down. Okay, and then same thing here. Let's square that, and again, I can pull it down. Quickly do the. I'm actually gonna. I think this should work. Okay, so I've just pulled those over, so I have the sum, and then of course the calculation where I take the square root of the sum of those sum of those square deviations and divide by 3, and I've got this 2.16. Okay, so we can do this by hand. Of course, Excel has certain things in there to help us out. And then to do correlation, again, this is going to be, so instead of squaring x minus x bar, we're going to multiply it by y minus y bar. Right? So we're, in essence, doing a two-dimensional, but it's not the same x minus x bar. Okay, so we're making we're rectangling it and not squaring it. Okay, and then excuse me, and then let's go ahead and just pull this over. We're going to add those up. So this is really the sum. Okay, and so we have 14, but of course that is not the correlation. I'm going to calculate the correlation down here, and remember, I have it written down below. So the correlation is that sum up top. I have this written wrong down here. I apologize. Should be the sum of. Oh no, yeah. Okay, so it's going to be 14 divided by n minus 1. So this is going to be 3 times then our two standard deviations, Sx and Sy. Okay, and we get 0.8366, which is exactly what we found last time. Okay, so we can obviously use Excel in these types of methods and to outline kind of our by hand work. But of course, Excel can do this, can crunch this for us by itself. And as you probably expect, we're going to go use that data analysis tool pack. Okay, so I'm going to grab correlation here. I might have it still plugged in, but oh, this is okay. So I'm going to grab the data. I'm going to select kids in milk here. Make sure I have labels in the first row clicked, and I'm going to put that up here. Okay, so a couple clicks, we get the 0.8366 without having to do all this gross work. Okay, so we can do things like correlation in later regression very quickly, but of course I'm forcing you to do it by hand often because it's important to know what this computer is doing in the background. So whenever you do regression, whenever you do correlation, you're often going to get these correlation tables, which along the diagonal is going to have correlations of 1. Okay, because what it's actually doing is it's correlating kids and kids. And if we have kids versus kids, the correlation should be 1, right? So anytime the kids increase, the kids also increase. Okay, so you're always going to see this kind of 1 and 1. But this is the value that we're after. Okay, so the other thing I want to do here is just to show, I think this will be easier to see than me scribbling it out, is that this is still a sample. Okay, so we're bringing with all the caveats of what happens when we randomly sample. And so the values that we churn out here are dependent on whatever the sample is we took. So if we play around with this data, and so I'm just going to do something, never do this, never change your data, but if we were to have taken a different sample, if we would have gotten a different set of families, and say for instance, we got a family of 8 that happen to be, let's say they're vegan and they don't drink any milk, that's going to alter our calculations quite a bit, right? So let me just redo that. So things to note, we can look at the scatter plot changing, but let's focus on that correlation. The moment I change one of these data points, this data point drops and the correlation drops to 0.4385. And so what I want to highlight is that, again, what we get out of this is dependent on what our observations are. And so when we think about a correlation, there is still that uncertainty around it, right? All of that uncertainty that we were dealing with in chapters 7, 8, 9, 10, 11, that's all with us here, in that we can't say for definitively that across all families everywhere that the correlation is 0.8366. Okay, that's the correlation for our sample. And so one of the sections that I actually I told you could skip, it was actually how we crunch those values or crunch, I should say, test whether or not this correlation is different than 0. And I have you skip that mainly just for the sake of time, and because that is not done often, because as we'll see, most of the time we're actually dealing in regression, and we have ways to test in regression as well. But the concept remains, and I think it's worth at least mentioning that when we find a correlation, it's dependent on our sample, and we could take this to let's see. So maybe this is if I had something like this, I can switch it around a little bit, and all of a sudden I have a negative correlation. Okay, so I've obviously chosen that specifically to manipulate the data, but the point remains that we could take a different sample, and it could lead us to a different result. So that's why it is possible to run a t-test and test whether or not the correlation coefficient is different from 0. And it follows much the same kind of logic and math as we've been doing. We're just not going to specifically do that for correlation. But we are going to do it with regression. Okay, so yeah. So let me see if I can back out of this manipulation that I did. I think I got it. Okay, so we're back to our original milk kids situation. And we've seen that that Excel can spit out a correlation for us. We're going to talk now about regression, and really what we're trying to do and how we do it. And in the simplest terms, as we talked about the other day, regression is finding that line through our data. Okay, especially in 2 dimensions here when we have just one x variable, which we're doing in chapter 13. It's really about where's that line that we've been trying to draw. Let me just see if this will work. That did not work. Give me 1 second. Okay. So really regression is there's some best fit line, and we'll talk exactly how we determine that in a second, but there's some best fit line. Let me see where I am out here. Try to do this blindly. There's some best fit line that fits through this data. Okay, it's probably not that. Maybe it's this. Okay, is it this line? Does that line fit best? Is it this line? Does that describe the data best? And so we're going to try to figure out how do we determine what line summarizes this data or these 2 variables best. Okay, so at the heart of it, that's what a regression is doing, and it's a linear regression. So same caveats as the correlation, that it's based on a linear relationship. We're not picking up any type of curvature, and we can talk a little bit next week about how there are other methods that try to incorporate that. Okay, now if you've played around on Excel ever, and maybe it's been 5 years, but the first time you plotted a scatter plot, you may have even done a regression without knowing it. Okay, so if you go into Excel and you are on a scatter plot and you simply click add trend line or trend line here, so I have to pick which one here, but we've just done regression. Okay, so or we've had Excel do a regression. So and that's of course as long as we haven't changed it from linear to something else. But odds are that some of you have done a regression without knowing it. And more specifically, if you've gone in there and added a displayed the equation on the chart, you've done regression. Okay, but now we're going to talk about what did we do? What did we just make Excel do? Okay, and more formally, we can have Excel do a regression that's not just this. We can have it actually spit out the real solutions. But my point is that this is something that you might have come across. So let's actually dig into what regression is doing. Whoa, all right. Guess that works. So so again, at the heart of it, regression is trying to best fit the data, and we have to make some choices as to what we mean by best fit. Okay, and what we're going to choose is that we're going to keep working with this same concept of squares. We're going to keep, and for much of the same reason, as we talked about back in standard deviation and now in correlation, the squared version, working with squares, has some pretty powerful and helpful mathematical results and ease of use, and it produces again what we consider unbiased estimates. Okay, so much like we're very concerned all the way along whether or not we have this bias built in, did we sample the divers by accident, too many divers coming out of diving practice for our height. We need to make sure that our randomization is done well to avoid that bias. Same thing here. We avoid some common biases if we use this squared version. Okay, so let me say at the outset, there's a lot of different types of regression, but the most commonly used and the most useful and probably widely applicable version is this one that we're about to learn, and it's called ordinary least squares. Whoops. Okay, so you may see other ones mentioned. Ordinary least squares. Okay, and so it really has to do with how do we minimize the squares? How do we get the least amount of squared values? Okay, and so this is all going to be back to deviations from the mean squared, and so you can see how or why why correlation is the foundation of this. Okay, and so I'm just going to redraw some of our actually let's just use a simple example with 3 data points. Okay, so how do I put a line in here that best describes the relationship between these two variables, so between the x and the y variable? Okay, and of course there are a lot of lines to choose from. Okay, maybe this is the best line. Maybe this is the best line. Okay, so how do we determine which one is the best line? And in reality, there are infinite different lines we could draw, right? We could shift each of these just slightly. We could draw in different kind of different slopes, all kinds of different lines. So the method that we're going to use is to compare the squared differences. Okay, so in some sense, we've been working with deviations from the mean. So you can think of this as a deviation from the line. Okay, so let me clean up to just one line here. So let's think about, I'm just going to redraw a slightly different line. Okay, so let's think about this line. This line obviously doesn't fully explain the 3 values, right? They don't fall right on the line. If we had 3 points exactly in a line, I guess we could draw that quickly. if we had 3 points that were exactly lined up, this is not a very difficult question. Right? We simply draw the line that runs through all of them. It probably has an R of 0.1 or 1.0. Our life is simple. But most of the time we have data points that are jumping around, and there's not a perfect correlation between them, right? So we don't have an R of 1.0, but we might have some type of a relationship that could be described in a linear sense. Okay, so the method that we're going to use is to look at the deviations from this line. Now we call that something different. We call it a residual. Okay, but we're going to measure the distance, and we're going to focus on the y value. Okay, so we're going to measure the distance between the line and each data point at the y value. Yeah, I think that statement was correct. Okay, so we're going to measure this distance here. Okay, so that's going to have some distance. We're going to measure that for all 3. Okay, and we're going to square each of these values. So much like we squared in standard deviation, we're going to do that again for many of the same reasons, right? We don't want to have these cancel out. And so we're going to square these. They're going to be positive values only, right? So this might show up as one of these might show up as a negative value, but when we square it, they'll be positive. And so we can just look at the total. So if this is, let's say this is a distance of 4. I'm just going to make these numbers up, but let's say that's 4, this is 2, and this is 1. Okay, so what we'll do, and we'll see that we don't have to go through this process. We have some techniques to avoid having to do all this math. But theoretically, this is what our math is going to have us avoid having to do. But this is going to be, so if we square this is really 16, right? Now, and this is going to be 4, and this would be still 1. Okay, so I'm just showing that we can think of it literally in terms of minimizing the squares, or minimizing the sum of squares. So your book eventually, as you're reading through it, will talk about minimizing the sum of squared residuals. Okay, remembering that this distance that we've measured is a residual. It's what's left over after we have estimated the y with our line. We said, yeah. So we're going to minimize these values, or the sum of this. Okay, so right now, what do we have? We have 16 plus 4 plus 1. So we have a total of 21. Okay, and so the question is this the smallest sum of squared residuals that we could have, or could we draw a line that's better than that? And better by, it would have a smaller sum of squared residuals, right? And so we're looking for what is the least squares. So we could draw a different line. Maybe we draw one in here that, so what's happened? We've gotten a little bit closer in this where we had the 4. Maybe we're the same, and maybe we got a little further on the 1. Okay, so maybe this is now, again, I'm just going to kind of make up some numbers, but maybe this results in a distance of 3, still 2, and now 2. Okay, so we could square those residuals. We'd get what? 3 times 3, 9. No, this is kind of unorganized, but we'd get 9 here. We'd get 4 and 4. And we'd add that up, and we'd get what? 8 plus 9 is 17. Okay, so the second line I drew with these made-up values has a smaller sum of squared residuals, and so we'd rather go with that line. We say that line depicts this data better. And we could keep searching, trying to find one that was maybe 16 or 16.8 or something like that, right? We could keep searching for a line that best fits the data. Of course, this is a never-ending process in our with doing this by hand, because we can always there's infinite number of lines. So we have a process that can get us there, and that's going to be based around our correlation value. But in essence, this is what we're trying to do, and this is what our math is going to show us, is what is the best line. So before we crunch this, and we can quickly crunch this for our milk and kids example, let's just rehash a little bit about what do we need for a line. Okay, and this is going to be kind of, rewinding all the way back to, I don't know when we first learned lines. But of course, what you've typically seen it as is y equals mx plus b, right? Where what? M is the slope and b is the intercept, right? And we need both the slope and the intercept to describe the line. If we don't have one, we end up with so if this is our line, we need both the slope and the intercept, right? If we don't have the intercept, then it could be any of these lines that are parallel, right? So the slope is telling us the rise over the run, but we need that intercept to know where it intersects the y-axis. Similarly, we need that slope because just having the intercept doesn't tell us which line we're on. Okay, so so we need in the way you learned lines, we need M and B. We're going to do the same thing, except we're going to change our notation a little bit. Okay, so we're going to deal with y is equal to a plus bx. Okay, where a is the slope and b is the intercept. That is not true. Please strike that from the record. Testing you. So a is the intercept and b is the slope. Okay, so if you're so b has changed. All right, so that's the big takeaway, is that b is not the intercept, b is the slope. We often, as we'll see, as you go through the text, sometimes we are talking about alpha and beta. Okay, one of which is, so the alpha and the beta refers to the population. What we're trying to estimate is an alpha and a beta. We use a and b for our sample. Okay, so much like so you can think of what have we been doing all along. The Greek letters have been the population values, mu, and when we talk about our sample, we're talking about x bar, not same with the s, right? So s versus sigma. So just we're sticking with the same thing here. So alpha and beta are referring to the population values that we're trying to estimate, and we're using a and b to work with our sample data. Okay, so we need to find a and b, right? So in order to describe this best fit line, we're going to need to find a and b. So much of what we do, your task in a regression problem is going to be largely you need to find a and you need to find b. Typically, what we're going to do is we're going to find b first, and then we'll be able to find a. So how do we find b? So b is going to be related to the correlation. Okay, so let's see if I can just pull up. Okay, it's going to be easiest. Let's get rid of some of this. And let's look at our data again. So in our milk and kids example, we found the following information. We found an R, a correlation of 0.8366. We also found SX of 2.58, and we found sy of 2.16, I believe. Okay, so that was the results from the other day, and that, of course, I won't fully plot that out, but remember we had a relationship, or a situation that looks something like this, right? We had some data points out there. And so how do we find B? Well, it turns out, and we'll just jump to the conclusion here. We can talk more about how this spits out later, but we get the following equation. I just want to double check that I'm using our book's notation, because you can describe this slightly differently. So B is always going to be, especially in our ordinary least squares version, how do we find this equation of the line? Well, it's going to be the correlation times sy over sx. Okay, so what are we doing here? So remember, correlation is the relationship between these two variables. But remember, correlation didn't have units attached to them, right? And that was one of the benefits of correlation, is that we can change units and still have the same underlying relationship. Well, some of what we're doing here when we multiply by sy over sx is we're putting units back in. Okay, so we're reattaching units to our discussion, and so now we can describe the slope, right? Because slope is dependent on units, right? Again, going back to your early math teachings of slope, is that we're really talking about rise over run. So as a person grows 2 inches, we can talk about weight increasing in pounds. So slope has units attached, and so that's what we're doing here with B. And so this is as simple as saying B is equal to 0.8366 times 2.16 over 2.58. Okay, and that's going to spit out the slope of our best fit line. So B, you can double check my math, but I believe we get 0.70. Okay, and so that is the slope of this best fit line. To attach there. Now I'm just kind of roughly drawing this because what we don't know what the intercept is. And so it could be right at 0. It's probably not. So I'm going to actually erase that because that could be confusing. So how do we find the intercept? Well, there's one other piece of information that I've kept secret from you if you haven't dug into the book yet, and that is when we're doing ordinary least squares, there's a quite handy result that falls out of it, is that the mean point excuse me, the mean point, the best fit regression line always goes through the mean. Remember, we plotted that before as a way to talk about values, whether they were both above or both below or opposite of each other in terms of deviations from the mean. Well, the best fit line is always going to run through that mean value. And so that's incredibly helpful when we're trying to figure out what the intercept is. Why is that? Well, again, remembering back to, so this is more algebra, not necessarily graphing, but when we have one unknown, one equation and one unknown, we can find that unknown. Right? So what have we learned thus far? We know now that y is equal to a plus 0.7 x. Right? That's the equation that we have thus far for this line. We don't know what a is. But we do know that the following is true. We know that this is going to be true. So this equation is true in general. Y is equal to a plus 0.7x. But it's also true at the exact point y bar x bar. Right? The line runs through that point. And so that must be a true statement. And so we can use our y bar and our x bar to find a. Okay, so this is, again, you know, as you anticipate having to do some homework problems, this is the process you're going to have to go through. Solve for b, plug b back into our y equals a plus bx, and then use that mean point to solve for a. Okay, and so our mean here is 4 is equal to a plus 0.7 times 7. Let's put that in brackets. Okay, so let's finish that out. 4 is equal to a plus I think this should be 4.9, right? And so, if I get out of the way, we now have found that a is equal to negative 0.9. Okay, and so we have found the intercept because it has to be true at that mean, and it's going to be true for every point. And so when x is 0, y is negative 0.9. And so we end up with the equation y is equal to negative 0.9 plus 0.7x. And I'm off the screen for some reason. There we go. Okay. And there we have it. We have found the regression equation. Okay. So it's as simple as that. Obviously, much of the legwork is to find the correlation, right? Once we have the correlation, it's a simple kind of plug it into two different equations, and we've got our line. So that's the equation of this line. Let's double check it. We're going to jump back to Excel here, and get out of the way a little bit. Let's see again what did we find in this equation. Again, plotting this, let's add in that line. And there we have. Now they're gonna write it a little different. Let me blow this up a little bit. So they've reversed it. They've got bx plus a, but obviously that's the same as y is equal to negative 0.9 plus 0.7x. Okay, so this is what Excel is doing in the background when you simply say, hey, add a line and then put a value on it, right? So in the simplest terms, this adding the trend line gives you that line, which is the regression line, the OLS regression line. Again, I'm just going to format the trend line and get that value back up there. I'm in the way. I'm displaying, which one is me? Okay. I'm displaying the equation on the chart. Okay. Also, you can add in the r squared. So we briefly talked about this the other day. Remember, that's just r times r, so 0.8366 squared is going to give us 0.7, so that also can be put up there. Okay, so let's look at more of why we might. Okay, so we've been working with this silly example, but now that we have Excel involved, we don't have to restrict ourselves to just to 4 data points. So let's look at some more interesting scenarios, and actually let's talk a little bit about why we might want to why we might want to use regression. Okay, so I'm going to just scroll over here, and I have some data on temperature and ice cream sales. Okay, still going to be a little silly of an example, but what do we have here? So maybe you run an ice cream stand. Okay, and you know that on average you sell 175 ice cream cones a day. Okay, pretty good business. But you have reason to believe that this is somehow connected to the temperature, right? Pretty decent guess. And so this might be able to help you, right? If we think about what do you need to do before you go out for the day, is that you need to maybe prepare a certain number of cones. Maybe you make the cones that morning, and so you want to know how many cones you should make, or how much ice cream you should take out of the freezer. I don't know, how do you do that, but maybe it's staff. Maybe you need to know whether or not you should hire your friend to come with you for the day or not. And so having a better guess as to how much you might sell could be incredibly useful. Okay, and obviously you can probably think of more real world examples regarding business, but let's stick with this kind of simple business example. So what we're going to see is that regression can help us predict a certain outcome. And that's one of the two big realms that regression is used in: prediction. The other one is that we can sometimes work on teasing out causal relationships. Okay, so what we're going to do here is we're not proving, in this example, we're not proving that temperature causes ice cream sales. Now, that might be a reasonable assumption, but we don't actually care if temperature is the driving force. We just want to know if we can better guess how many ice cream sales we're going to have. Okay, so without the temperature information, our best guess is that any day we're going to sell 175 ice cream cones. So can we do better with this added information? So I've plotted the data here. Okay, and we can see what we expected is that there seems to be some positive relationship between ice cream sales and temperature. So what a regression line can give us is what should we guess for any temperature? Okay, so we have this data. Maybe this is the past few weeks, the past 2.5 weeks. And let's say we know what the temperature is supposed to be tomorrow. Can we make a better guess than 175? And the regression is going to give us that. Okay, and so when we go through the process, and I'm going to just jump over here. So if we jump over to the correlation tab, we'll just speed up through a few of these examples, because I just want you to be able to see kind of the end results. We can do the same crunching of correlation, right? So I have that here, what we just did with the milk and kids. We can get correlation of 0.72, which is, probably what we expected. We can have Excel do that for us. And what I want you to see here is now we can do the regression based solely on what we've done. Okay, so remember, B is simply R. I'm very zoomed out. I apologize for that. We can zoom in here a little bit. And just shrink a little bit. Okay, so what we're after is this regression equation. So what is the best fit line between temperature and ice cream sales? And so we can find that using our correlation that we've just calculated. So 0.722 times SY divided by SX. Okay, so if we do that, and I have that plugged in here, we get a B of 2.73. Right, and then of course we need to find A, we need to plug it into the equation where we're going through the mean, right? So the same thing we did with the milk and the kids. The mean was 4.7. Here we have a mean of 175 and 76, and so we can find A by plugging in 175 equals A plus the B we just found times 76, and that's going to give us a value of negative 32.7, basically. Okay, and there we have found the regression line. So I have it written down here. And that can be incredibly useful. Now, I don't have the... Just jump back and look at this ice cream sales. Of course, we could add the trend line. Okay, and I'm going to go in and add the equation. make that visible. Okay, and there we have those 2 exact values we just did. Okay, so we don't have to go through the by hand process, but that's what we're doing. That's what Excel is doing. Okay, so let's jump over and have Excel do that for us. Sorry to jump around so much if you're getting dizzy. So we have, again, here I have the data up here again. You can ignore the temp too. Apparently I was playing around with squaring the temperature. So ignore that for now. That's a leftover from I don't know what I was doing. But again, I have the scatter plot up here. This time I've added that mean point, so we can just know again that what Excel's doing or what the regression is doing is always going through that mean point in this version of regression. Again, there are other types of regression where that's not necessarily true, and the process for finding A and B are going to be a little different. But we won't cover those here, and in fact, they're just deviations from this same underlying concept. Okay, so if one thing I want you to know is that if we've understood regression now, but if you go and look at some research paper or something and you see them using a different form of regression, and you say, okay, I thought you have to do this process to find the regression results, you can think of it as in chapters 10 and 11, we talked about those decision trees in terms of do we know the population standard deviations? Can we assume they're the same? If we can, it's one version. If we can't, it's another version. Same thing with regression. Sometimes there are decisions that we have to make that lead us to deviate slightly from this OLS version, the ordinary least squares version. But at the heart of it, it's doing the same thing. And also, when you see somebody use a different form of regression, they almost always will also report this version of regression. So even when the decisions lead us to a different regression to use, we report these because it's so widely used that people want to still see what did the OLS show. Yeah, just a way to highlight that this is heavily used. Okay, so we get so Excel can do this for us again with the data analysis. Now we're going to have Excel spit out a lot of information, so more than just what's on the scatter plot. And the reason for that is that a lot of what we do with regression is test whether or not something's different than a certain value, often 0. Okay, so like I said, we can do with correlation, test whether or not that correlation is different than 0. We can do that with Excel, okay, and we're gonna be forced to do that in the text and do that by hand, calculate those, testing the slopes. But it's all based around a t-test. Okay, so same concept as we've been working with. We just have to apply it to a new situation. Now, what I want to show you is that Excel's output gives you the results of those t-tests. Now, you still have to go and do this by hand, and I'm going to force you to do this kind of incrementally, so you have to do it by hand. But I also want you to know how to interpret it from Excel. So I have that output here. So set that aside. We're gonna recreate that here. So I'm gonna do the data analysis tool pack, and I know we're kind of speeding through some things, but I want you to be to have seen this at least a little bit before we come back next week. So I'm using the regression. Okay, so in the data analysis tool pack, I'm choosing regression. Okay, and I'm going to grab the Y input. So here, I want ice cream sales. Okay, X input, I'm going to do temperature. We're going to use the same method when we talk about chapter 14 and doing multiple regression. So we can have more than one X. I have labels going on. Do I want any of these others? I do not. I just want to put this down here somewhere. I think that's okay. So we'll just do that. It'll spit out some kind of basic output. And what do we have? We have we are going to get exactly what we got. So we had 2.73 and negative 32.9. We get 2.73 and negative 32.9 or 69. Okay, so this process spits out the equation for that line, but it also gives us our t-stats, right? So these are the t-values, and it's giving us what? It's giving us p-values, okay? And over here, we're actually getting confidence intervals around that, those p-values. Or sorry, around our coefficients. Okay, so a couple things. We call these coefficients. This is the coefficient on the intercept, and this is the coefficient on the temperature. So we'll talk more about interpreting this, but this is where you want to start looking. We have the values to describe our line. We have our t-stats, which we've been typically calling t-values throughout the course, and then we have p-values. Okay, so we have everything we need. We have the number of observations. We have our this is the r-square. And so on. Okay, so we can talk more about how we interpret those later, but I want you to know that this is here for us. And yeah, so I think we'll leave it about now. We'll be back next week, but I'll also have a video up talking more about interpreting these. But we'll talk more about how we can use this to predict. Okay, so again, one of the goals is that we want to know how many ice creams are we expecting to sell today. And so this can help us down that road. So if you haven't started digging in, please start digging in. This is a big, thick topic, and we're only starting to scratch the surface of it. And so, yeah, I'll be around later today at office hours. So if you want to jump on in, feel free to do that. Otherwise, we'll talk to you soon.